I'm the NI VeriStand Product Manager and the Real-Time Test Software Group Manager. And today I'm going to walk you through the introduction to NI VeriStand. We're going to talk about what it's used for and what comes with VeriStand, as well as how to use the power of the National Instruments platform to extend the functionality of NI VeriStand. So, when we talk about NI VeriStand and when we use it, it's really used for what we call real-time testing applications. And at the very basic definition, it's using a real-time operating system to perform a test. And those usually fall into three general categories. Embedded software testing, where we're using simulation and closed loop mathematics to perform ECU or embedded software test. The most common application in this area is hardware-in-the-loop testing. And this is really where VeriStand got its roots and where it started. And we're also going to talk about test cell control systems, so using a closed-loop system to test something mechanical, so a dynamometer or an actuator tester. And then the third area where we've seen VeriStand used more commonly is these high channel count condition measurement systems. So maybe many channels of data acquisition, such as a structural tester or a fatigue tester. So let's take a look at these different types of applications and walk through the similarities and the differences. So in an embedded software test, in this case we've got a hardware-in-the-loop test system. Where the device under test is on the right. You can see it's an engine ECU or an automotive ECU or an electronic control unit, and we're testing it against a test system here that does stimulus generation and logging. We're logging the data in the closed loop system, and we're providing stimulus, so we're essentially driving the ECU. And we're also doing mathematical simulation or electrical simulation. So we're connecting our ECU to maybe a PXI system that's running a simulation model that represents maybe the engine or the whole vehicle to virtually drive the car. And then we're providing stimulus to actually run the tests and doing logging. So when we transition that now and we go from a pure electrical simulation in embedded software testing and we look at test cell control systems now the device under test goes from an electrical device such as an ECU, and now it's a mechanical test system, or mechanical system I should say. In this case it's a dynamometer for a very large vehicle. But you can see a lot of the components are the same. So we're still generating stimulus, so we're still driving the car, we're still doing lots of measurements and logging. We still have this closed loop control system, but now instead of an electrical simulation, it's a physical simulation now. So we're doing PID control or load control on the actual dynamometer that's driving the car. So we're telling the car how fast to go, and we're providing a physical load on the wheels of the car, or in the wheels of the truck in this case, to represent the road conditions. So driving up a hill or down a hill, we control the reverse torque on the dynamometer to drive that car. But the rest of the test system is very similar architecturally. So you can see that there's a lot of overlap between embedded software test and test cell control. And then when we move into condition measurement systems, we oftentimes will break the system into two pieces. We'll still have some sort of control, and we'll still be generating some sort of stimulus to stress test, in this case, an airplane wing. The difference here is that oftentimes these are separate boxes that are doing the control, and in the NI system, in this case, is just doing the measurement and logging. So architecturally, the systems are very similar, but they're often, when it comes time to implement these systems, they're often split up into multiple pieces, and the control can sometimes be very sophisticated. There may be a third-party system doing the control because it's something that's kind of outside of the core NI strength, and we would just do the logging. Now there are situations or applications where we'll do the control as well, but they'll still typically be in two different systems, two physical boxes. So when we look at these three different types of applications, there's a great deal of overlap in the requirements and the types of functionality that these applications require. You can see there wasn't a great deal of difference at a high-level architectural standpoint. It stands to reason that there will be a lot of overlap in the types of functions that they require out of their software. Things like stimulus generation and data logging, you saw those on the pictures. Being able to automate tests, perform hardware I/O, all of these things are required. And then sometimes you'll have either simulation or a closed loop control. So there's a lot of these common requirements with regards to what software elements that need to be in these types of applications. And that's where NI VeriStand comes in. So we built NI VeriStand to cover the common elements that are present in all of these different types of applications. And we built it in a way that's scalable across all of our hardware products. So anywhere from a Windows PC that's running pure simulation through large distributed multi-chassis systems. The largest distributed system that I've seen to date is a 27 real-time PXI chassis system connected together with reflective memory using NI timing and synchronization modules. So VeriStand is designed to give you a lot of the basic functionality that you need right out of the box. So for some applications, a customer may be able to just pick it up, use it with a PXI system, for instance, do some data I/O, import a simulation model, and be able to get up and running very, very quickly. What we recognize, though, is that these applications are often very sophisticated and very complicated. So it stands to reason that there will be some functionality that the customer needs that VeriStand doesn't have out of the box. For those cases, VeriStand was really designed to be extended and functionality have added to it using things like LabVIEW and simulation models and FPGA. Nearly every layer of the VeriStand software, we've provided hooks or plugins that are available so that customers can customize the functionality of VeriStand to meet their needs. We're going to talk about more of that later on in the presentation. We'll talk about exactly how customers can do that. So now we're going to look at a high-level view of what happens inside of the NI VeriStand engine. So the picture here is a snapshot of what's happening in the real-time system. So when you deploy a VeriStand system, this is what runs on the real-time PXI system. Okay, so these are things like hardware I/O and model execution, all of the things that need to run deterministically run inside of this VeriStand engine. And what you see on the right here is a high-level picture of how the system is actually architected. So you can see that you've got your primary control loop, which is your main loop. It's your high-priority thread in the real-time system. So that loop needs to run on time all the time. And that's the VeriStand architecture is built in such a way that loop will run on time if it's possible. And everything else will take a lower priority. So then you've got other things like model execution loops and communication loops and other things like that. And all of these loops communicate with each other through what we call the EU array, which is it's a real-time database, or it's a big lookup table. So we deposit data values into this real-time lookup table, and then we retrieve those data out. So in this way, we're enabled to pass data through the real-time engine, and this is also the way that we pass data up to the common user interface that I'll show you here in just a second. So why would a customer want to use VeriStand for their application? One, it reduces the time for development. So a customer could do everything that VeriStand does. They could build it with LabVIEW if they needed to, but VeriStand is really it's a LabVIEW built application that's designed to get customers up and running much faster. So many of the things that the customers would develop on their own, VeriStand does out of the box, and that lets the customer focus on the elements that might be missing. So they spend less time doing development because the architecture is built for them. And then once the system is up and running, this is something that a lot of customers don't think about. It's the maintenance associated with that application. So customers oftentimes will think about the challenges associated with developing the system, but they don't necessarily think about, well, how do I upgrade the system, and how do I maintain the system over the course of time? Because the VeriStand engine is an NI supported application software, we add features to it every year. We're committed to a yearly release cycle, And it essentially takes the burden off of the developer. Right? If their end users have questions about the software, they can call National Instruments and get answers, as opposed to that developer answering all the questions related to the software. So it really removes the long-term burden from our customers by having this real-time architecture predefined. So this is exactly what the folks at Embraer found valuable. So this particular application is the Legacy 500, which was a small commercial jet, or a small private jet, actually, that they developed the System Integration Lab, or Ironbird, using VeriStand. So they used 27 PXI systems connected together, as I mentioned before, communicating to perform a large-scale simulation in a large number of I/O points. And this was the second time they had done this integration lab. The first time they had built everything themselves, and the first time they went through this process, the integration, construction, and development took them 42 months. Using VeriStand and NI products, the commercial off-the-shelf technologies, they were able to complete the Ironbird in 30 months. So by using COTS tools and VeriStand, they were able to cut 12 months off of their integration lab development cycle, which is a very, very big time savings. Now this case study is available online. You could see it. There was actually a really good video with Guilherme Sealander from Embraer, just explaining how they built the Ironbird, as well as the benefits that were provided. And this is another really good example of customers understanding the value of VeriStand. So that, again, this is a smaller integration system, but it was an application that required testing of 6 ECUs. And using VeriStand, they were able to break up the system, the physical system, into different submodels and test all 6 ECUs essentially with one PXI system. And it enables them to extend the functionality and the performance of the HIL system as their needs changed. So this system actually started as a 4 ECU tester, and they were using a competitive product or a product from another vendor, but that product couldn't be expanded or extended. Using the PXI system, they were easily able to add a couple of cards and go from the 4 ECU tester to the 6 ECU tester. And this case study is also on our website, and you can share this with your customers anytime you need. All right, so looking back and going back to how VeriStand is built. So we already looked at what's happening in the real-time part of the VeriStand engine. So that's the bottom. That's the hardware I/O and the model execution, things like that. What actually happens is that VeriStand sends data back to a Windows-based user interface, and today we call that the workspace. So the box on the bottom, again, that's what's running in real time on the PXI system. The box on the top is what's running in Windows. So all of those things are user interface elements. So we can do calibration. We see all the live data getting updated. We can manage and configure system alarms. We can do automation. We can configure model parameters, so essentially to batch execute updates on model parameters to change the personality of the real-time system. We do all of this from our user interface. And the way that the user interface, or the workspace, and the real-time engine are connected is through that little blue arrow you see there, and it's a TCP IP link and a UDP link, so 2 different Ethernet-based protocols. And they're connected basically through just these 2 pieces of communication, sending data back and forth. The nice thing about that is one, it means that you can make changes to your user interface without having an impact on your real-time engine. So the 2 pieces are entirely independent of one another. So you can create GUIs, add elements, make changes to the user interface without shutting off the real-time engine. This is kind of a unique thing in the NI product world, because that's not something that we can do with any other tool. And the other thing that it enables you to do is it enables you to close the UI and run the system headlessly. So the VeriStand engine, once it's deployed, will keep running even if you close the UI. So if you wanted to run batch tests overnight, for instance, you'd be able to take your PC home with you, and the VeriStand engine could run all of your tests, and then when you came back, you'd be able to plug that back in and see the results of all your data. So it's a very, very useful and nice way to do the HMI or user interface to real-time engine configuration. And we have examples and videos that show you how to configure these systems and run them on ni.com/VeriStand/demos. So if you're interested, take a look at those videos. Now, we're talking about the out-of-the-box functionality, and you get a lot with VeriStand out of the box. I want to share a story with you about an application where a certified LabVIEW architect, Greg Sussman, had the opportunity or had the choice to make, and it's the question was, well, do I build this HIL system from LabVIEW from scratch, or do I use VeriStand? And now Greg's a certified LabVIEW architect, so he's certainly capable. And what Greg found was that it just made sense to use VeriStand as a starting point. Now in this case, we didn't use VeriStand to replace LabVIEW. We used LabVIEW and VeriStand together. And this is really the power of VeriStand, because in this case, Greg started with VeriStand and it gave him a lot of the functionality that it needed, and then he added functionality to it using LabVIEW. So he was able to focus on the things that needed to be added to the framework in order to be successful in the application. And this is a very, very powerful thing, and it's kind of a philosophy that we've adopted. We call it configuration-based extensible with LabVIEW. And again, in this area, LabVIEW is the biggest differentiator for VeriStand because it allows us to add this functionality as we need it. So now let's take a look at how we can add this functionality. What are the different ways? So we'll go ahead and take a look at everything here. So again, we're looking at our two big blue boxes. And so the VeriStand engine, again, that's what's running in the real-time PXI system or Compact Rio. And then we've explained what our workspace does. The workspace is our GUI, our user interface. So real-time engine is running in real time on the PXI. The workspace is running in Windows, and we're able to see that. But you can see everything on the right. Those are all of the different ways that you can plug your own custom code into VeriStand. So you can create your own FPGA IP using LabVIEW FPGA, and you can plug that into VeriStand and run it and execute it. You can plug a large library of simulation models into VeriStand. We'll take a look at what's all on that list. We'll take a look at that in a minute. And then there's this idea of a custom real-time tasks, or we call them custom devices. And that's basically any sort of real-time code that you want to add to the VeriStand engine to do a variety of different things. You can add that using LabVIEW. And then on the user interface side, the entire UI is customizable. So you can make your own UI objects. You can also make your own tools menu tools. So if you want to have a service running in the background, or you want to create a pop-up window, you can do that inside of the workspace. And then the things along the top, these are ways that you can automate VeriStand, or they're ways to plug VeriStand into a higher level application software. So nearly everything in VeriStand has a .NET-based API to go with it. So if you wanted to use TestStand as your high-level automation software and just call VeriStand in the background, the .NET APIs enable you to do that. That's a pretty common thing that we do today, and a lot of our customers do that. We've actually made a lot of investments to improve and to make the TestStand VeriStand integration as seamless as possible. And you can do the same thing with things like Python or .NET or even LabVIEW. So all of these things are able to call VeriStand and automate it and run it. So if you wanted to make your own custom user interface, you could do that, and VeriStand would really just act as a hardware abstraction layer or maybe a simulation engine. But you're not limited to just using the VeriStand UI out of the box. You can create your own UI. And this is something that's growing in popularity, especially when it comes to the TestStand VeriStand integration, because the two tools work so well together. So now let's take a look at some of the different ways that we can plug things into VeriStand. So one, FPGA. So I don't think we need to talk a lot of depth about the value, the benefit of FPGA, but here are some common things that you would use FPGA to incorporate inside of VeriStand. So engine simulation, sensor simulation, things for automotive or really for any HIL application. You may want to do FPGA-based simulation of these sensors and actuators just because of speed or latency requirements. You could also make your own protocol. This is pretty common for some application or for some industries that don't really have a common protocol set, where it's kind of required that they set their own protocols. And then the last one is that this is becoming more and more common, is sometimes simulation models need to run really, really fast, and a processor-based system just can't keep up. That's where this ultra high-speed simulation comes in. It's mostly common right now in the area of electric motor or power electronics simulation. So what we did is we partnered with JMAG, which that company is a Japanese company that does computer design of power electronics or motor systems. So this is a tool that motor designers use to actually develop and build motors. Historically, the simulations associated with that design tool were meant for pure simulation. It's really designed to understand the response and how a motor will act if they build it in a certain way. And the models are very computationally intensive, so they take a long time to run to get very limited amounts of simulation data. So we're thinking about if in the past, if you were to use the JMAG tool to do a simulation, it may take hours or days to do mere seconds worth of simulation. Very, very computationally intensive. What we did with JMAG and adding that to VeriStand is we basically encapsulated or incorporated their simulation models onto our FPGA. So now those models will run in real time. This was a technology that didn't exist before, and it was very, very successful, and it's a very useful tool. And we used it at Subaru. If you were at NI Week last year or have seen the case studies, you know that Subaru was a very strong lead user for us. And in the past, they had to do all of their testing, all of their motor testing on a dynamometer because the simulation and the HIL capabilities weren't there. Using this new FPGA-based technology and the JMAG tools, they were able to move a lot of their testing from the dyno into the lab. And what that really meant for them was that they reduced their expected development and test time to 1/20th. So they cut off 95% of their test time based on moving from the dynamometer into the HIL lab. So this is a great success story. Again, this case study is available on the NI website. You can see the video where the folks from Subaru are explaining the benefits of FPGA-based simulation and using the NI tools for HIL. All right, so I'd like to move on to the real-time functionality. So we talked about FPGA. Now this is how we want to plug in real-time code. So anything that you need to do, whether it's talk to a third-party instrument, add some custom real-time functionality, maybe for some sort of data logging or triggering application, or really anything that we need to do, maybe creating a custom protocol that we need to communicate over, anything that's not in the VeriStand engine today, you can use LabVIEW real-time to add that functionality to VeriStand very easily, or out of the box. So it requires a fair amount of LabVIEW knowledge, and it requires we recommend certified LabVIEW developers add this functionality, but you can add any sort of functionality that you need. So when customers ask me if VeriStand is capable of doing nearly anything, I can almost always say yes, because you're always able to write these custom devices and these custom plugins. We have a library of add-ons that are available in various places. We've got a couple of add-ons that are available on edit.com/VeriStand/add-ons, and those are the ones that we support and we maintain, and people can just download them and use them. They're very high quality add-ons. And then we have a VeriStand open source community on GitHub, as well as the NI VeriStand Add-Ons community page on edit.com, where we keep open source IP that customers can use and build. Now, it's open source, so they'll have to compile it and build it. So oftentimes it's useful to have a partner or NI integration person help with that build. But the code's all there, and it's a very good way for customers to get up to speed and learn how to do these types of custom devices. And you see, there's all sorts of different things that are available right now, ranging from switches to power supplies to third-party devices, even up into things like machine vision. So many different things that our partners and our systems engineers have built over the years, and it's available for our customers. An example of this, we won't spend a ton of time on this, but an example of this is the Engine Simulation Toolkit. Now this is one of those toolkits that's available on ni.com/VeriStand/add-ons. and it's an FPGA-based toolkit that's imported into VeriStand, and the communication layer is plugged in through a custom device or a real-time code. And this enables us to do all sorts of things that an engine hardware-in-the-loop system requires. Pattern generation, replay, angular processing, so we're able to measure or simulate where the engine is in its rotation. So all sorts of different real-world requirements for doing engine simulation. And then we can essentially simulate as many engines as we want because of the scalable architecture of this toolkit. Again, this is available for anybody doing engine control HIL. This is a really useful toolkit, and I strongly recommend it. This is a great example of the community and the add-ons that are available for VeriStand. I want to spend a little bit of time talking about simulation models. For HIL applications, simulation models are absolutely necessary, and VeriStand is very good at importing simulation models from a variety of places. The customer can compile their model from many places into C code and then build a DLL, and then you can import that DLL inside of NI VeriStand. So it's very handy and useful that way. And we've got some shipping examples that come with NI VeriStand out of the box. We've got a sine wave generator, and we've got an engine simulation that comes with VeriStand, so you can actually see the code and see how it's built. And then you can see how we import it into VeriStand. So essentially you have inputs and outputs that are defined inside of the model, and then a whole bunch of parameters that are used to characterize the model. And we're able to interact with all of those different points and pieces inside of VeriStand. And here's a list of the real-time modeling environments that we support today. The most common that I see is the MathWorks Inc. simulations or simulation software. We also obviously work with LabVIEW and a variety of other tools. And most of these tools and these modeling environments are driven by customer requirements. So oftentimes a customer will ask for support for a certain simulation model, and then we work with that model vendor to add the functionality to VeriStand. So we publish a model framework that tells these modeling companies how to build their models, and then they incorporate and build in the automation associated with building their model into C code and building the DLL, so that the customers have a very seamless and helpful experience. And the continued support is maintained by our partners. So all of these other modeling environments do the routine support to make sure that their models work inside of NI VeriStand. Again, so if you have a modeling environment that's not on the list, you can feel free to call or contact National Instruments or contact me, and we can work to add that functionality. So we've got a couple of pieces, OpenMedoc and FMI. Those are things that we're working on today, but we can always add more. And LabVIEW models are a way to import some very nice functions into VeriStand. It's a pretty seamless process, and it works on our PXI-based systems, our FarLab controllers. So really all you need to do there is in your VI, you wire up the connector pane, and you tell LabVIEW whether it's required or optional. And then there's a tools menu option where you basically just tell LabVIEW to build the model for VeriStand. You select it and you hit the build button, and then you have your model, and then you can go ahead and import it. So it's a very easy way to add custom functionality to VeriStand, and it could be a basic PID controller, it could be a math function, or it could be a complete characterization or mathematical model of a physical system. All of those things are available and very easy to export from LabVIEW. And any model that works with VeriStand can be imported and used in LabVIEW using the LabVIEW Model Interface Toolkit. So this is great for doing some quick model testing or getting models into LabVIEW. If you're a LabVIEW developer and want to do that, the entire framework is built and maintained, and it works for both LabVIEW and VeriStand. So any model that works in VeriStand also works in LabVIEW. And the last thing I wanted to touch on are the APIs. So VeriStand has an extensive .NET API library that enables you to automate and control VeriStand from a variety of sources. Anything that can communicate with a .NET reference can be used to automate VeriStand. And we wrap up the more commonly used functions inside of LabVIEW VIs as well. So there's a whole VeriStand palette inside of LabVIEW when you install VeriStand. And you can do things like communicate with the workspace, automate custom devices, fault some channels, monitor alarms. So there's all sorts of different things that you can do with LabVIEW VIs that are used to control VeriStand. There's an even more extensive list of .NET APIs that are used to using .NET references inside of LabVIEW. So it's a very extensive list, and we've had many customers who've been successful automating VeriStand using either LabVIEW or TestStand or anything that needs to communicate through .NET. All right, so I hope this has been helpful. I want to review with you kind of the benefits of VeriStand. Again, VeriStand is designed to reduce development time by providing an architecture that works out of the box. You can do a lot of the functions that you would need to do for a real-time testing application, things like simulation and hardware I/O and stimulus generation. VeriStand does all of those things out of the box, so it should help reduce and shorten the development time. And then once the system is built and running, it reduces the maintenance cost and the long-term support burden on developers, and you get yearly upgrades associated with VeriStand, so you get new features for free as we do development. So you get a lot of extra benefits even in your existing HIL or real-time test system. So ideally, it's going to help you up front and then help you in the long term as well. If you want to know more, if you want to learn more about NI VeriStand, NI.com/VeriStand has video demonstration, tutorials, webcasts. It's got links to our add-ons community. So there's really a lot of resources and information available on NI.com/VeriStand. And then there's an NI.com/real-time test. There's a demonstration that walks through how to use VeriStand and TestStand and Diadem and Requirements Gateway together to create a comprehensive test environment that really takes you through all of the different phases of both embedded software verification as well as physical testing. So it's a good demonstration on how to use all of our tools together for a really comprehensive test system. Thank you for your time, and thank you for your interest in NI VeriStand.